Hello, my dear students. Welcome to Module 6 of Engineering Geology. Today we'll discuss the geotechnical investigations and evaluation for tunnel alignment. In this module, you will know about various underground openings, especially the tunnels which are going to use for transportation. What are the different types of tunnels? What are their parts? What are important geomorphological and geological investigations to be carried out for safe construction of tunnels? And you will also come to know about different support measures which are installed for safety of the tunnels. We will start with introducing the underground openings. We may have different kinds of underground openings. For example, when we go for underground mining, we make a lot of excavations, we make drifts and edits, we make irregular opening inside the ground. But for transportation, we use tunnels to pass any natural obstacle on the ground, or sometimes we go for making tunnels to ease out traffic congestion, especially in the cities where we go for tunnels which are under the ground, mostly used for railways. Nowadays, in our own country, we have a lot of projects which are metro projects, wherein we have gone for construction of lot of underground tunnels. We can also use tunnels in place of bridges. They are termed as subaqueous tunnels, and we also use tunnels to carry water from the dam sites, from the reservoir to the hydroelectricity generating units, that is up to the turbines. Today we will be discussing mostly on the transportation tunnels. Now, for transportation tunnels, we have to have proper alignment, we have to have proper size. The decision for alignment and size depends upon that how big is the natural obstacle. Normally, when we go for road construction in the hilly areas, there we may not need many number of tunnels. We need few tunnels to pass through the hills. But when you go for railway tracks, there you need lot of tunnels, because railway tracks cannot be bent suddenly. They need a curvature onto which the rail can turn. But in case of roads, what we can even have hairpin bends on which the road can turn at very sharp angles. So the number of tunnels normally we found more along the railway tracks as compared to the roads. If you go for part of tunnels, we have two very important parts or three very important parts of tunnels. We call portal, that is the upper part of the tunnel. Then we have floor of the tunnel, which is also called as invert. And then we have adjoining walls. Most of the tunnels which we have, they are arch shaped tunnels or horseshoe shaped tunnels. Tunnels can also have square cross sections. Tunnels can also have circular cross sections. Most of the water pressure tunnels which carry water from the reservoir to the turbines for generating hydroelectricity, they are circular tunnels. Most of the tunnels which are made in soil or earth, they are usually square section tunnels. But tunnels in the rocks are mostly arch tunnels or horseshoe shaped tunnels. The most important part of tunnel is the portal or back of the tunnel, that is ceiling of the tunnel, followed by the walls of the tunnel and then the floor of the tunnel. Now there are different associated part of the tunnels. For example, if you have this hill which is to be crossed by tunnel, then we also have some extra excavation. For example, you may have to have a vertical opening which is used for shaft, which may be used for carrying men or carrying machines. Sometimes we may have some small diameter shafts which may be used for ventilation. So we may have different kinds of opening related to the tunnels. If you are having metro tunnels, then associated with the metro tunnels are the railway platforms, railway stations, which are bigger and rectangular openings. Now for construction of tunnels, we have to go for excavation. Now depending upon what kind of tunnels we are going to make. Are we going to make tunnels in the rock? Then it is called as hard ground tunneling. Are we going to make tunnel in the soil or earth? Then it is called as soft ground tunneling. In soft ground tunneling, we go for construction method which is called as cut and cover method, wherein we excavate first, then we put foundation of the floor and wall, then we erect wall, and finally we put slab over the walls, and that is the covering of the tunnel. And then the earth which we have excavated out, that can be filled back over the roof of the tunnel. So this is called as cut and cover method, which is used for soft ground tunneling. When we go for soft ground tunneling, we have some problems associated with this tunneling operation, which is mostly related to the earth failure. These earth failures may be in the form of raveling ground, where the earth start falling as chunk from the vertical walls. We have problems of squeezing ground, wherein moist soil wall start squeezing in to the opening. We can have flowing ground, where we have flowage of water with the soil or sand or clay, or we may have incursion of groundwater if we happen to cut the groundwater table while excavating. In hard ground tunneling, we normally opt for mining method. This mining method is a very old traditional method, wherein rocks are excavated after drilling and blasting. So there are different stages of this excavation, which starts from marking of the holes where drilling has to be done. After drilling, they are charged with explosives and the blast is carried out so that rocks are loosened. These rocks are excavated. The process of excavating rock is called as mucking. We give sometimes for gases which have been trapped into rocks after explosion, or the gases which were already trapped in rocks to go out, that is called as a recuperating stage. After mucking and recuperating stage, we create the opening, and then if there is any need of support, then we go for installation of support in the opening. Nowadays, machines have been much in use for excavating through the rocks. We have different kinds of machines which excavate through the rocks, specialized for shaft boring. We call shaft borers. We have boring in which we start from tunnel upward, that is called as raise. So we have raise borers, we have rock headers, and most importantly nowadays we have a machine which is called as tunnel boring machine, which can be used for excavating through the rocks of diameters from 7 to 9 meters. These tunnel boring machines, they are very costly. So what we do when we have to excavate tunnels more than a kilometer, then we employ this machine, and this machine also has a provision for installation of concrete circular support. So nowadays tunnel boring machines, they are in much use as far as excavation through the rocks are concerned. Now the role of engineering geology comes when we go for hard ground tunneling, because in hard ground tunneling we have lot of problems, which is, for example, falling of rocks from the wall or the roof, that is called as spalling ground. We may have issues of popping of rocks, that is rocks breaking and popping into the opening. We can have issues of blowouts, because the rocks in which excavation is made, sometimes they are under high stress. So when we create opening, those stresses, they start getting activated, and this results into the generation of very small magnitude earthquakes because of breaking of rocks. So that is called as blowouts. Apart from this, we also have problem of squeezing ground, problem of swelling ground, depending upon what kind of rocks we are excavating into. So hard ground tunneling is a difficult tunneling. Now we have different issues related to the geomorphology and related to the geology of the area in which excavation is made. Now geomorphology comes into play because it is going to control the morphology of the topography above the tunnel. Wherever we have high ground, the load will be more as compared to areas where there is valley. So the load in this section will be high as compared to this section. But if you have a valley fill, then we will have problem of seepage in this part of the tunnel. So geomorphology is very important because it is going to control the overall load on the different sections of the tunnel. If we are making tunnel through any hill, if you go close to the slope, then the problem of rock mass movement will be very high. If you make your tunnel through the mid of the hills, then the length of the tunnel will be increased. So we have to see all permutations and combinations to have safety of the tunnel from the earth surface processes, or processes which are related to the landslides or mass movement, as well as we have to ensure that the tunnel length is not very high, because we can optimize in the length of the tunnel. So by default we will be optimizing on our economy. As far as geological considerations are concerned, there are various aspects starting from rock type, weathering state of the rock, structures present in the rocks, the presence of groundwater in the rocks. All these are going to have profound control in the construction of tunnels. If you have sedimentary rock sequence, the rock will be somewhat weaker, you may need more support, but the ease of excavation will be more. The rate of advance of tunnel excavation will be more if you have softer rocks. But with softer rocks, we will have lot of problems. If it is sedimentary rock, for example, then we may have chance of lot of groundwater. But if you are working in igneous rocks, the rocks are massive. There, the rocks are very strong. The rate of advancement of tunnel may be slow, but your tunnel will be much safer. Similarly, in metamorphic rock, if it is non-foliated metamorphic rocks, then the tunnel will be much safer as compared to the tunnels in the foliated metamorphic rocks. In fact, the very first engineering classification of rock mass, which came in 1947, given by Carl Terzaghi, was related to the 9 classes of rocks which he has identified, and then he given the different support measures for these 9 classes. As far as structure of the rock is concerned, the attitude plays very important role. What is the strike and dip of rock with respect to the tunnel length? Now we can have different permutations and combinations. We can have horizontal rocks, we can have vertical rocks, we can have inclined rocks, we can have rocks inclined towards exit of the tunnel or towards entry of the tunnel. The rocks may be inclined towards right side of the tunnel or left side of the tunnel. Now when we go for tunneling in horizontal rock, it is somewhat safer. But in the case of vertical rocks, the overall load comes onto the ground if you compare it with the horizontal rocks. If you have rocks dipping towards you, then the tunnel excavation is termed as drive against the dip. If the rocks are dipping away from you and you are excavating for tunnels, then it is called as drive with the dip. The drive against the dip is difficult and dangerous as compared to tunnel drive with the dip. We can also have issues related to the thickness of rocks. Higher is the thickness of rock, less will be the rocks coming along the tunnel. If you have thickness of the rock very less, then we'll have multiple rocks coming along the tunnel length. So it all depends that what is the thickness of the rock, what is the width of the tunnel. Sometimes you may have a situation wherein tunnel width is less than the thickness of the rock. Rocks are striking parallel to the tunnel alignment, then all through the tunnel you will have same rock. So tunneling in same rock is much better option, much better condition as compared to tunneling in different rocks. Sometimes we may come across with a folded sequence of rocks. Now again we have to see that what is the relationship of fold axis with tunnel alignment. If we are parallel to the fold axis, then we may have our tunnel along the anticlinal zone or along the synclinal zone or in between the two as per the situation, as per the alignment, as per the location. But if we are going for excavating tunnels across the fold axis, then you will have anticlinal zone and synclinal zone both at different locations depending upon the wavelength of the fold. Now if we make tunnel along the anticlinal axis, then because the anticlinal zones, they are under tensile stresses, we'll have lot of fracture system and it will be easy to drive tunnel through the anticlinal zone. But we may need lot of support. As against this, in the synclinal zone, the rocks are under compressive stresses. There, the driving tunnel will be difficult. But because of less number of fractures, the tunnel will be much safer in the synclinal zone. But synclinal zone has a problem of groundwater. Whatever groundwater is seeping through the fractures in the rocks, they will get concentrated along the synclinal zone as compared to anticlinal zone. So we have to see that what is the best option left with us. It is better to have tunnel in between the two, that is anticlinal zone and synclinal zone. In the mid part of the limb, if we can drive a tunnel, that is the best option. Then we can also have faults along the tunnel alignment. We have to avoid those locations where we have faults, especially the active faults. Because if you have active fault, that fault may get rejuvenated anytime and that will result into the destruction of the tunnel. But if you have faults which are dead faults, then again we have to see them, because along the fault we have lot of crushed rocks. So the seepage problem may be there. So we have to, if we have to go through the tunnel, if we have to have our tunnel through the faults, then we should take those faults at 90 degree so that we can have minimum of them. And the rocks which are present as a crushed rock, crushed zone, that has to be excavated out and it has to be backfilled by concrete or reinforced concrete. Shear zones, they are very common. The presence of shear zone will always be a problem because the rocks will be much weaker along them. They may also have lot of groundwater. So we have to check them, we have to seal them, we have to excavate them, and we have to backfill by the concrete. The most important structure which we have, that is the joints, which are ubiquitous. They will always be there. The presence of joints, they are actually going to have overall control on the behavior of rock mass as far as tunneling operation is concerned. Depending upon how many sets of joints we have, what are their spacing, what are their orientation, it is all going to affect the tunneling excavation and post tunneling operation, because we have to seal all these joints and fractures. In fact, all the rock mass classifications which we use for predicting the rock mass behavior, they are actually governed by the joints and related parameters. For this, we have to go for overall analysis, starting from unconfined compressive strength of the rocks to the RQD, that is rock quality designation. We have to analyze joint spacing, joint condition, joint alteration, and ultimately we may have to use two of the important rock mass, any two of the important rock mass classification, that is rock mass rating system or rock mass quality system. All these rock mass classifications, they have incorporated all these important factors related to the joints. Now we have two different concepts which are prevailing as far as construction of tunnel is concerned. One is New Austrian tunneling method, which is also known as NATM method. In NATM method, it is being said that when you excavate the rock, and if there is a destabilization of rock mass because of excavation, we will allow that destabilization and we will allow the rock mass to readjust itself to the present stress distribution condition. As against this, we have another method that is called as Norwegian tunneling method, NTM. In this method, what we do not allow any displacement of rock mass. We immediately support the rock. We preempt its behavior by employing different rock mass classification system, and we install the support before any deformation takes place. So we have these two important concepts. Now when we excavate, we have to provide support depending upon the rock mass quality. The traditional old support system was based on the presence of wooden leggings, wooden frames, wooden posts and sills which were installed in the rocks in different pattern, and then steel came, and then steel arches have been used for supporting. Nowadays, apart from steel arches, the support system is mainly based on rock bolts which are 2 to 5 meter long. They can be installed through the boreholes into the rock mass, and they can take load up to 60 ton. Sometimes if we have very weak rock mass, in fact before excavation, we first install rock bolts in spilling fashion just outside the required diameter of the tunnel, and then we go for excavation and we leave those rock bolts therein. Depending upon rock mass quality, we may go for full face excavation. That is, we are going to excavate the whole dia or whole face of the tunnel, or if the rock mass are weak, then we can go for benched excavation. Depending upon the importance of the tunnel, depending upon the diameter of the tunnel, we have a relationship between what is called as equivalent dimension, which is related to the span and excavation support ratio. From this we calculate equivalent dimension, and this equivalent dimension is plotted against rock quality, rock mass quality, that is Q system, and we have standard graphs which will provide the requirement of the support system. So we may have rock bolts, we may have steel arches, we may have shotcretes, we may have fiber cretes. All these, what will be the thickness, what will be the spacing, what will be the length, all these can be calculated with the standard graphs present which equate the rock mass quality with the equivalent dimension. There is always an issue of overbreak and underbreak. When we go for excavating tunnels, for example, this is our required tunnel dimension. When we go for excavation, especially by drilling and blasting techniques, at some places we may have overbreak, and in some cases you may have underbreak. So both are these issues are not required, because if you have overbreak, then you have to backfill by concrete, that is up to the required diameter, that is called as pay line, which will incur extra cost. If you have underbreak, then you have to go for again excavating by some method. So this problem of overbreak and underbreak has to be resolved, and pay line has to be decided. This overbreak is mainly due to the presence of weak zones, or sometimes due to the extra concentration of joints, or sometimes due to the presence of layers. So just to understand the rock mass class and ease of tunneling, when we go for tunneling, we need some time in the opening to carry out the provision of support. Now, for example, if we can relate the two most important engineering classification of rock masses, that is rock mass rating system of Binyavsky and rock mass quality system of Burton. Now, if we have very good rock class. That means that in RMR system it will have a value of 81 to 100, and in Q system it will have value more than 40. Then this kind of rock mass has average stand-up time of 20 years for 15-meter span. That means for 15-meter span there is no need of any support because the stand-up time is very large. But if you have good rock condition where RMR value is 61 to 80 and Q system value is in between 10 to 40, then the 10-meter span has got a stand-up time of only 1 year. So if you just see that as rock mass quality deteriorates, the stand-up time suddenly goes down, even for a smaller span. In this case, you may have to install spot bolts wherever it is required. If you have fair rock condition, that is class 3, where RMR value is 41 to 60, Q system has value from 4 to 10, then for 5-meter span, the stand-up time is with 1 week only. So it is very less time for 5-meter span. If you increase the span to 7 meter or 9 meter or 10 meter, then the stand-up time will further get lowered. There we have to install pattern bolts. That means all along the opening, in the back of the tunnel, in the wall of the tunnel, we have to go for pattern bolting. Class 4 rock, which is also termed as poor rock, where RMR value is in between 21 to 40, Q system value is 1 to 4, the 2.5 meter span has got only 10 hours of stand-up times. So in this case, we have to install lot of rock bolts, pattern rock bolts, plus we have to go for thick, short plating. And the last class, that is very poor rock mass, class 5, where RMR value is less than 20 and Q value is less than 1, even 1 meter span is going to fall within the 30 minutes. So this is the poorest rock mass condition wherein we can go for construction of tunnels, and there we have to employ or install steel ribs, and that too at a very close spacing. So sometimes actually what happens, that if you are tunneling, for example, for 1 kilometer of length, you may come across with any of these rock mass classes. Very good rock mass you may find good rock mass. You may also find fair rock mass. You can have poor rock mass and very poor rock mass if you are crossing any shear zone or fault zone. So within a tunnel, we may have probability of having different conditions. That's why it is said that as far as tunneling operation is concerned, you have to design as you go, be ready for the worst and hope for the best. In our own country, we have hundreds of tunnels which have came up in last 75 years. One of the very famous, very old Jawahar tunnel in Jammu and Kashmir, which is 2.5 kilometer long. Here in this table, I have shown only those tunnels which are more than 2 kilometer long. Recently, last month, a tunnel was opened in Jammu and Kashmir, which was a road tunnel. It was inaugurated by the Prime Minister Narendra Modi. This tunnel is 9.28 kilometer long. But the longest tunnel in India we have, that is a rail tunnel, that is in Pir Panjal mountains, again in Jammu and Kashmir, from Cheril to Munda, which is having almost 11 kilometer of length. Apart from this, along the Konkan railway, we have many tunnels, and these tunnels, they have length varying from 2.5 kilometers up to 6.5 kilometers. So most of the Indian important tunnels, they are all along the railway routes. We have very few tunnels along the roads. If you go from Kalka to Shimla, we have almost 103 tunnels. So along 90 kilometers of length, we have more than 100 tunnels. The longest one is perhaps 1.5 kilometer in length. To summarize, I can say that the construction of tunnel is one of the very difficult tasks because it involves a lot of issues. starting from the planning stage to the selection of the site, alignment, selection of machines, logistics, selection of persons for designing the tunnel. Lot of expertise is needed. Then we have to have lot of workforce. We have to supervise the operation, and the most important thing is the coordination and communication amongst different stakeholders, different level of workers, and it involves a lot of punctuality and dedication. Incentives to the workers, facility for personals have to be there. In the case of any emergency, we have to have proper hospital system, etc. Then what is most important is that what is the advance per round of excavation. This is going to tell us that how much time we are going to take in completing any tunneling operation. So for this, what we have to see that what is the total actual working time on daily basis, on weekly basis, on monthly basis, and then what was the breakdown time. So from actual working time, we have to deduce the break time, and then we have to see that what is the exact rate of tunneling operation or actual advancement in the construction of tunnel. This is a work which is almost blind. We do not have any idea that what is going to happen, how our work is going to install. So we have to have a very good investigation before planning stage, where engineering geologists have to play a very important role. Thank you.